Hello, morning.
Good morning, sir.
Good morning,
Good
sir.
morning, sir.
Yeah, so good morning to you all. So yesterday we were talking about ground improvement technique by vibroflotation. So there is a small part which is remaining in with regard to vibroflotation technique. So let me explain all those details and let me give one or two examples also. Uh, Regarding the design of vibroflotation, once the ground has been improved, so then how do you ascertain that the desired degree of improvement has been achieved or not? So for that purpose, normally the compaction degree is measured in the form of the relative density, is normally measured in the form of a relative density. The basic reason is that the vibroflotation technique is fundamentally ideal for sandy type of the soils. So when you talk about the sandy soils, so the relative density is only the measuring parameter to ascertain the degree of improvement. So therefore, we normally measure the relative density as shown in this formula. So how much should be the degree of relative density value? So that we have already discussed in the yesterday's class. Now another important design parameter is a test pattern. So what kind of the test pattern we shall select so that whole of the ground is equally improved. So when you go for vibroprotection technique, a couple of the patterns has been shown here, but once you suggest a particular pattern, it is the requirement to have some kind of a test section to affirm the same thing. So therefore, once the designer is submitting his design guidelines, then on the site, the field engineers must reassess again and find it out which will be the optimum grid spacing and what kind of the pattern they should follow really in the ground. So that is what is a test pattern. A couple of the test patterns are shown here. Now, as I discussed yesterday, to ascertain the degree of improvement, normally we will conduct either standard penetration test or cone penetration test. So in case of the vibroflotation, the cone penetration test is widely used. So to measure the degree of improvement. So this is some more information on depending upon the foundation or the footing type. So how many number of uh, probes must be inserted into the ground. So this part also we did discuss in yesterday. So just a recapitulation, and there are one or two important points. So the zone of compaction around a single probe will vary according to the type of vibrofloat used. So we have also seen in the design aspects the spacing has been related with the vibrofloat, the frequency of the vibrofloat or the capacity of the vibrofloat or vibroprobe. So we have seen D. Apollonia as recommended all the guidelines based on the 30 HP vibroprobe, while Webb they have taken into consideration of 100 kilowatt. So the cylindrical zone of compaction will have a radius of about 2 meter for a 23 kilowatt unit and about 3 meter for 75 kilowatt unit. So this clearly makes you understand the influence of the probe capacity on the density or the zone of influence. As you increase the capacity of the probe, so there is an increase in the density in the radial direction or in the, the lateral direction. So this simple schematic explains about how to ascertain there was no soil which was unattempted or unimproved. So this is a probe spacing between center to center, and this outer circle indicates the zone of influence. So these are the further details different people have suggested based on their field experience about different configurations or patterns. The spacing, distance and pattern affects the uniformity of the densified material. So as is true from the right side schematics. So if you judiciously not choosing the spacing, then we may leave some kind of the void. so which may create some kind of non-uniform or differential settlement in the subsequent times. So rectangular and square patterns, spread footing, or for small isolated area of the improvement. So if you look at this pattern, this can also give some kind of an idea depending upon footing requirement, how many number of probe locations one has to select, so that the zone of influence of the whole footing area is under the ground improvement zone or the zone of influence. So it is recommended that normally, so equilateral triangular pattern is the most efficient for the ground improvement. So in fact, uh, in terms of the performance, the triangular pattern is the highly efficient, but often we may also go for other patterns like a rectangle. So as I was explaining, CPT is one of the basic tests to ascertain the degree of improvement. But how to correlate the CPT values with the relative density? So this graph as prepared by the different people, so which is a relationship between the relative density versus the cone penetration value. You can see QC is the cone penetration value, so which has been normalized with effective overburden pressure, that is sigma V naught dash, and it has been related with the relative density. So how do you use this chart is, once the ground has been improved, so by adapting to vibro flotation technique, now on the post compacted ground you try to conduct a CPT test and keep on getting the results of the cone penetration. So normalize this with the increase in overburden pressure, so initial overburden pressure, that is sigma V naught dash. So then try to understand or pick up the value. So pick up the value. Say for example your QC by sigma V is say 200. So then draw a vertical line and draw a horizontal line to the ordinate. So this will give you the approximate value of the relative density, so which is an indicative parameter of the degree of improvement. So there are some different mathematical correlations also proposed by the different people. We can see one kind of an empirical equation, so relating relative density with the cone penetration value. There is another kind of equation, so relating the relative density with the cone penetration value. There are some other constants also, C1, C2, C3. So these constants normally are the functions of the empirical equations, are the parameters of the empirical equations. So if you are interested, then these constants can be further correlated with, for example, the soil type or the gradational characteristics, or so on and so forth, depending upon the important parameter that affects or influences the ground improvement. So people normally do such exercise for modifying the empirical equations. So these are the further correlations, as we can see here. As we were discussing in the previous slide about different constants C1, C2, C0, C1, C2. So C1, C0, C2. Here the correlations were proposed between cone resistance QC and vertical effective stress sigma naught, and as a function of the relative density for different values of the constants. This is left consolidated sand with K naught of the earth pressure coefficient value of 0.45, while the bottom right side graph is same relationship, that is cone resistance versus mean effective stress. However, this is valid for normally and over consolidated sands. So this is the above graph is valid for normally consolidated sand with the earth pressure coefficient of 0.45, while the bottom graph is valid for both normally and over consolidated sands. So you can use these charts as some kind of a predefined charts to ascertain the degree of improvement in the form of a relative density. Now I couldn't able to explain properly yesterday about the volume change. So let us try to have a little more discussion on how to relate how to relate the subsidence with the volume change. Subsidence is nothing but the net volume change.
Sir,
Yeah,
sir, like you said that the relative density is defined, desired relative density after compaction, we know like 60%, 75% in like that
correct,
cases. So
correct.
this relative density will correspond to which depth means because when we do the cone penetration test, we will get different values of relative density with depth.
Yeah, it's a good question. So let us look at this graph now. Okay. So for example, if you look at this graph carefully, as going deep, your cone penetration resistance increases. Consequently, there is also increase in the sigma v value, that is initial effective overburden pressure. So both numerator is increasing and the denominator is also increasing, and both have an kind of an interrelation. That interrelation is related to the relative density. Okay, just imagine yourself, the QC's remain same. For example, you take a site where we need to improve the soil from 0 to 20-meter depth. So imagine before compaction, your QC value is almost same from 0 to 20-meter. But your sigma V value keeps on increases because this is nothing but gamma times of a Z. So before compaction, even though there was no improvement in the QC value, but there was a linear increment of initial effective overburden pressure. So that means almost constant value of the numerator, there was a linear increment of the denominator. So therefore, there is a variability in the value of the QC by sigma V naught dash. But if you observe the same, the ratio of QC by sigma V post compaction, there is an improvement in the QC and the sigma V's remained same. So therefore, that improvement in the QC is getting normalized with the improvement in the sigma V. So therefore, ultimately, if the degree of improvement is uniform from 0 to 20-meter, you should almost get more or less close values of QC by sigma V. So when there are a close values of the sigma QC by sigma V, which obviously indicates a uniform degree of relative density. You got it now? Did you observe, did
Yeah,
you understand?
yes, sir, yes, sir.
Okay, very good. So let us try to understand about how to calculate or how to relate the subsidence. So we have taken the case one where the volume change is measured without the backfill. So the left side figure is the initial condition. There is a volume of, there is a solid and there is a void. The AE is the area are nothing but the area of the zone of influence. V naught is the initial volume and there is a subsidence equal to S. So but the zone of influence area will not change before or after, and but the final, there is a change in the volume. So V naught is the initial volume and V1 is the final volume. So there is no change in the volume of the solid, but there is a change in the volume of the void. So initially it is Vv and finally it is Vv dash. So the change in volume is nothing but Vf. So which is nothing but the equivalent area multiplied by the subsidence. So if you express these changes in the voids in terms of the empirical equations or the volume mass relationships, so we can correlate the change in volume to the initial volume minus final volume. So Vf is nothing but V naught minus V1. V naught minus V1. So the same thing has been expressed in equation this 3.26. E into S is nothing but, so this is the initial volume and this is the final volume. E naught is initial void ratio, E1 is the final void ratio. If you simplify this equation, then this can be re-expressed as Vs into E naught minus V1. But what we are doing in the field is we are improving the ground to a depth of, therefore the is nothing but, so the influence area multiplied by the total depth, this total depth. So which is again nothing but the Vs into 1 plus E naught, that is initial area, Vs into 1 plus E naught, initial area. So this is simple making equivalent to the volume mass relationships. Now if we divide the equation 3.26 by the 3.27, then we will come up with the relationship between the amount of the subsidence occurring over a depth of h, and which is related to the change in void ratio. E naught is initial, E1 is the final void ratio. Okay, so you can use this equation to calculate the probable subsidence the post vibroflotation technique. So that's why, because you know the depth of the improvement, that is h, we can able to determine the initial void ratio before compaction, the final void ratio after compaction. So therefore only unknown parameter is s. So once we know the initial final, then we can determine what would be the probable subsidence that has been occurred after compaction. Now let us take another case where the creation presented with the Vf. So almost same change in the volume mass. However, the void created is backfilled with the quality aggregate materials. So here also the final volume is nothing but initial volume minus the final volume. So the change in volume that can be expressed as Vs into E naught minus E1. So dividing this equation, because here we are dealing with the backfill. So in the previous case we dealt with only the without backfill. So dividing equation 3.27. So 3.27, that is the initial volume of the entire equivalent area, A into H. This is 2.27 by 3.29. So this is the final volume. So then we can get AE into H divided by Vf is equal to 1 plus E naught by E naught minus 1 naught. So this is simple mathematical jugglery. However, now here our interest is to calculate how much volume of backfill material is required. In the earlier case, our interest is to determine what would be the probable subsidence. But in this case, since we are backfilling the void, so we have to have a clear understanding about how much of the backfilling material to be brought to the site. So in order to calculate the amount of the backfill material, we can use these analytical equations, these empirical equations. So this Vf can be related to the column or the cylinder which is forming during the vibroflotation technique. So the Vf is nothing but the pi by 4 into d square into h, where d is the diameter of the column that is forming after backfilling. But we did discuss during the design the equivalent area, that is the zone of influence area, is also related to the pattern type that you are adapting to. So for example, you may adapt a triangular pattern or you may adapt the rectangular pattern. So accordingly, the influence area or the equivalent area can be related to the spacing. Take the rectangular, so then AE can be written as S square. If it is a triangular, then this can be 0.866 times of S square. But AE we have expressed in the previous equation as pi by 4 into d square into 1 plus E naught by E naught minus E1. So when you rearrange the terms, then we can determine what should be the optimum spacing of a column. So the simplification of the equation 3.32 can give us the spacing determination equation, that is for a square pattern or the triangular pattern. So in case of the square pattern, it is S square. In case of the triangular pattern, A is equals to, this is 0.866 times of S. So then upon rearrangement, we will get these two forms of the equation. Now if there is a ground subsidence or the heave, because when you do, there is a probability of the small heave or the subsidence is inevitable after the vibrocompaction. So let us try to correlate the subsidence or heave with the spacing. So that's what has been done here. So suppose if there is a ground subsidence or heave after vibrocompaction, the required volume of backfill is Vf is equals to A into, this is small h, not capital H, A into small h, E naught minus E1 by 1 plus E naught. So just the same equation, plus or minus A into S, where S is the depth of the subsidence. So here there are two signs, plus or minus. So plus can be used if you observe a heave, minus can be used if you observe a subsidence. So then combining the equations 3.31 and 3.34, so this equation, so we can get the most sophisticated equation for computing the spacing of the columns. This is equals to this one. The equations 3.33 and 3.33 doesn't take care of either subsidence or the heave. While if you also want to account for the subsidence or the heave that has occurred after the vibrocompaction, then you should use the equation 3.35. Okay. So these are some empirical equations given by some people, so that I will like to present. So I request you all to note down this sum, how to calculate the subsidence. So a 5 meter thick loose sand exists on a site that has a fines content of 8% without any clay particles. The minimum and maximum void ratios of this sand are 0.456 and 0.950 respectively. So this sand has an initial void ratio of 0.673. The design requires the sand to be densified to a target relative density of 75%. A large horsepower vibrator such as HP 100 is available for vibrocompaction. Estimate the required spacing of compaction points in a triangular pattern and the average ground subsidence after vibrocompaction without backfill. So please note down. So this statement of the problem embeds a lot of information. So first of all, the thickness of the soil strata to be improved is 5 meter. So this is a loose sand. So when you say it is a loose sand, loose deposit, there is a probability that it can undergo large settlement. And they have also established the gradational characteristics of the sand and found that it has a fines content of 8%. So this 8% is less than the 12%, because when we did discuss about the applicability of the soil type, so we elaborated that the fines content should not exceed 10 or 12%. So therefore the 8% is less than 10%, it is okay. So the vibrocompaction technique is valid. So incidentally, this soil doesn't have any clay particle. So therefore no problem. Then they have also measured the void ratios of the sand. Initial void ratio is 0.456, as you can see here. The final void ratio is 0.95, hoping there is a huge change in the void ratio. So this change is attributed to vibrocompaction. So 0.456 means a loose deposit, 0.95 means dense deposit of the sand. So this sand has an initial void ratio of 0.673. Okay, so this 0.456 determined in the laboratory, but the in situ initial void ratio is 0.673. So if you closely observe, one thing is clear. So your natural void ratio is in between maximum and a minimum void ratio, Emax and E minimum. Next, the initial void ratio is 0.673, but the maximum void ratio that can go is 0.456 that we can reduce. So that means there is enough scope to reduce the white spaces. The design requires the sand to be densified to a target relative density. So the target relative density has been given as 75%, and the features of the vibro float has also been given. That vibro float, that is 100 HP, and estimate the required spacing of compaction points in a triangular pattern. So they themselves has fixed they want to go for the triangular pattern, and so you also need to calculate the subsidence, that is S, the subsidence value. So after vibrocompaction, so without backfill. Yeah, can I go for the solution? So did you all note down? Hello.
Yes, sir.
Yeah. So can I go for the solution?
Sir, one doubt.
Yes, sir.
Yeah. Please ask me.
Sir, at the edges, ironing is not required in this method.
No, here ironing is not required because there is no formation of the crater. Na? Whatever the crater is forming, this is by default filled with the backfill material during the compaction itself.
Okay.
Okay. But rather, uh, we can go for some kind of a blanket layer. It's not ironing, but they put a one layer that is called as a blanket layer.
Okay, sir.
So first, our target relative density is 75%. This is fixed. Then if you recall, so this is the graph proposed by D. Apollonia, Webenhall and Brown. And this is for a triangular pattern. As you can see, this is valid for a triangular pattern. So, and our relative target density is 75%. So it is a triangular pattern. So it is quite clear. So there are three number of probe locations. Then the influence coefficient from the figure. Select dr, that is 75%. 75%. So draw a vertical line onto the relative density line. So this diagonal line is nothing but relative density line. This diagonal line. So draw a vertical line from the relative density of 75 until it is intersecting the diagonal relative density line. From the intersection point, draw another horizontal line. So until it is intersecting the ordinate on the right side. So at the intersection point of the ordinate, the approximate value of the influence coefficient is 12.5. 12.5. But we are going to use the triangular pattern wherein three number of probe locations are involved. So as per the guidelines, the 12.5 shall be divided by three number of probe locations. So the value of 12.5 is contributed by three compaction points. So therefore, the influence coefficient corresponding to each compaction point is 12.5 divided, that is 4.2. That is 4.2. Now, in the next step, what you need to do is select or identify on the right side ordinate the value of the 4.2, and draw an horizontal line onto the proposed curves by the different people onto the curves. So here we have selected the typical application. So therefore, an horizontal line has been drawn from the 4.2 until it is touching the curve. So from there, you drop another vertical line onto the x-axis, and identify the intersection point. Identify the intersection point. So here this value is approximately 1.7 meter. So from the influence chart, we could able to determine that the optimum spacing is 1.7 meter. Optimum spacing is 1.7 meter. So this is how we should use the chart for determining the optimum spacing. Now, if you look at the chart carefully, and if you look at the triangular pattern, there are other parameters also has been given, where S is the spacing between center to center locations of the two probe locations. This is a triangular pattern, equilateral triangular pattern. Suppose if you want to calculate the vertical height, that is 0.866 into S. So where S is 1.7. So we can calculate what is the vertical distance. Or you can also calculate the center distance, this is center point from the centroidal to any location, that is 0.577 into S. So this 0.577 and 86 based on the simplification of the triangle, that is geometry. Okay, so this you can do additionally. So now our relative density dr is 75, and corresponding to which we should calculate the wide ratio. So all wide ratios has been given. Now our target density is 75%. We know the Emax value, we know the E minimum value. So therefore we can calculate what would be the probable change in wide ratio value, that is E1. So from the same relative density equation. So E1 is nothing but that is the natural wide ratio post compaction. So E1 is nothing but Emax minus dr into Emax minus E minimum. This is simplification of relative density equation. So E1 what we are getting is 0.58. Now we have an initial wide ratio of 0.67 and the final wide ratio of 0.58. So even this one also even lower than the E minimum, that is 0.45. So we know the equation relating the subsidence with the overall depth of the improvement, that is S by H is equals to E naught minus E1 by 1 plus E naught. So here the total improvement depth is 5 meter. Total improvement depth is 5 meter. E naught is initial wide ratio that has been given as 0.673, and the final wide ratio required for relative density of 75% is 0.58, and initial wide ratio is known. Substitute all the numerals and try to calculate the probable subsidence. So the probable subsidence is 0.279 meter, approximately 1 feet. So in a nutshell, if you try to adapt vibrocompaction on a 5 meter thick loose sand, so we can anticipate a subsidence at the ground level of 1 feet for this wide ratio. This is most important for that wide ratio because the subsidence is highly related to the change in wide ratio. Yeah, so this is what all about the vibrocompaction. You can ask me if you have any kind of a questions. So I do hope that I have covered almost every aspect of vibrocompaction to the best possible.
Sir, if we have a square pattern,
Yeah, it can
uh,
have a square pattern.
in that case, is there any direct relation between this graph values and for square pattern?
There is, this graph is also useful for square pattern. So in that case, here instead of 3, you should divide the influence coefficient by 4. That's it.
Okay.
Because let us look at, since you are asking a question, suppose if you are getting the same 12.5 influence coefficient value, and what is happening to the spacing, let us try to understand. Suppose if I go for the triangular pattern, I am going to get 1.7. Okay, suppose say I'm going to use the square pattern for the same thing, then 12.5 divided by 4, that means what I will get is around 3 plus something. So 3.1 we will get it. So corresponding to 3.1 to 3, so 3.1, if you drop a line, then the spacing increases. You can see. So corresponding to the influence coefficient of 3.1, and if you draw horizontal line and project it onto the x-axis, then what you get is approximately 1.85 meter or something. Your spacing is increasing.
So does that mean it is more economical?
We do not know. We cannot talk about the economy because we have to ultimately understand about the performance.
Okay, sir.
Good. So, any other questions? Yeah, questions, please.
Sir,
Yeah.
sir, can you explain the test pattern concept again, sir?
Test pattern. This one.
No, sir. Yes, this one, sir.
Okay. See, theoretically, so we have proposed some particular pattern, say triangular or rectangle, but we were not having any kind of an idea whether the same pattern, same spacing works in the field or not. So for that purpose, what normally we do is, depending upon the importance of the project, we do some kind of a preliminary testing in the field. So to affirm or to confirm that the spacing proposed is okay and the pattern also works or gives high performance. Okay, so here we can see these are the different patterns. Pattern number A, here they followed all triangular patterns only, triangular patterns only, but for different spacings. A, B, C. So 3.1 meter, 3.4 meter, 3.7 meter, 4, 4.3.
So after doing all these patterns, they take out the relative density and check in which we get the maximum one.
Correct.
Okay, sir.
So any other questions? Okay. So I will stop it here. So let me